Okay, so we're on page 3, and the function is x cubed minus 6x squared plus 3x plus 10, and I've typed it into the calculator already. Then it says to find the coordinates of the x-intercept and the y-intercept. So remember, y-intercept really easy. It's a couple ways to do it. The second table is the easy way. X equals 0, y equals 10. So the y-intercept is 10. Both my pens are green. Okay, so the y-intercept is 10. And the x-intercepts we can find by doing second calc 0. And then we put the left boundary here on the left side of this intersection. Then we put the right boundary here on the right side, and we do guess. And one of them is negative 1 comma 0. Oh, I forgot to start plotting the points, but I can just plot the points now. So negative 1 comma 0 is one of the points. And I already said that y equals 10 is one of the points. So let's put y equals 10 here. So we'll do the scale so that this is 0 and this is 10. And then we will do the next x-intercept, which is here. We'll do second calc 0, which is number 2. And then we'll do the right boundary over here. And 2 comma 0 is another x-intercept. And finally there's this x-intercept here. So we'll do, from the looks of it, they always cross on integers. So let's look at the table and see if maybe the table can tell us the third one. Yeah, it's 5 comma 0. Okay. This is 5. And so like part of the graph looks kind of like this. And then it goes down, and 4 comma negative 10 is another point. Okay, so I'm thinking that it goes below that, but let's look at the max and the min points, because it says write down the coordinates of the turning point. So let's do that. The way we find the turning points is we do second calc minimum and maximum. So we'll do maximum first, which is 4, and then oops, let me redo that. Second calc maximum, and then I need to put the left boundary to the left of the maximum, enter. Put the right boundary to the right of the maximum, enter, guess, and the maximum is 0.268 comma 10.4. So let's put that there. So it would be 0.268 comma 10.4. Let's find the minimum. Second calc minimum, which is number 3. And then we'll put the left boundary here on the left side of the valley. And then we'll put the right boundary here on the right side of the valley. To guess. And the answer is 3.73 comma negative 10.4. That's about here. So 3.73 comma negative 10.4. So if we were going to graph that, it looks kind of like that. Okay? Alright. Write down the coordinates of the point of rotational symmetry. I forgot to talk about that in the investigation. So the way you can find this middle point of rotational symmetry is you could take the midpoint of the maximum and the minimum. Okay? So what you could do is you could take the average of 0.268 and 3.73. So let's do that first. Because finding the midpoint, you basically take the average of the x's and you take the averages of the y's. So 0.268 plus 3.73 divided by 2. So that would be the coordinate, which is, it's basically 2, right? So I think that the midpoint is this point right here. Okay? So that is the point of rotational symmetry, or the which would be 2, 0. And we already knew that was an x-intercept too. So the x-intercepts, oh, we forgot to answer x-intercepts. So the x-intercepts are -1, 2, and 5. And the turning points I wrote down on the graph. Write down the coordinate of the point of symmetry, the point of rotational symmetry, it's 2, 0. And how did I do that? I found the average of the x coordinates of the max and the min. That should give me, in theory, the point exactly in between the two. And I didn't even need to find out the y, because I already knew that if the x coordinate was 2, then the y coordinate would be 0, because I already know that's an x-intercept, right? D, the graph is reflected in the y-axis. Write down the new equation. Okay, so when you reflect things in the y-axis, remember how when you have the a parameter for parabolas, it turns the thing upside down. So if your a value is negative, it turns it upside down. So the way you can get the negative version of this graph here is you just make the whole thing negative. So basically, your reflected graph would be negative f of x, which is equal to negative x cubed minus 6x, or plus 6x squared, because we're going to take negative of everything, like that, okay? So minus 3x minus 10, okay? All right. And let's go to number 2. A section of a toy roller coaster is in the shape of a cubic curve with equation blah, 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 where f of x is the height in meters. Plot the graph of y equals f of x. Okay, so I'm going to type it in here, and then I'll be right back. I'm in the middle of typing this function, and this is a useful thing that I've showed before in other videos, but just to remind you, if I need to put in a fraction 35/6, if I don't want to use a bunch of parentheses, I can use the math number and then go up, and I have the n/d option, which allows me to put in fractions kind of vertically, and then I don't have to put parentheses around the top, around the bottom, or on the whole thing. So I just can put the thing in without parentheses, which is pretty convenient. Okay, so I've just put in this function, and now I'm going to plot it on the calculator at least. All right. And then I'm going to get some useful points to put it on my graph here by using table. And by the way, just I forgot to note that, you know, this point here is y equals 10, so this point here would be y equals negative 10, right? And I did not also make axes, which I should put. Right. Okay, for the axes for the bottom, when I look at the graph here, do you see how mainly I'm working here in the first quadrant? So I'm going to put my axes like this, okay, and then I'm going to look at the table to get some of my points. So for example, -1 comma -3, that's like off my screen, right? It's down here. 0, 5, that's here. 1, 9, that's here. 2, 10, that's here. 3, 9, that's here. 4, 7, that's here. 5, 5, that's here. What else? 6, 4. 7, 5. 8, 9, 9, 17, and 10, 30. Okay, so that is my function graphed. Find the local maximum and minimum values of this function. So in this particular case, I believe that the maximum and minimums are here, but just to make sure, we'll do second calc maximum. Where, oops, and the right bound is over here. Oh, actually, it's not there, is it? Okay, so it's a good thing I tested that. So the maximum point is actually right here, and the maximum point is 1.92, comma 10, 10.0. Okay, 10.00. It's like slightly more than 10.0. Okay, that's why it's the one of the points is 2 comma 10, but 1.92 is on the other side. Oops. It's actually here. Okay. All right. Then I'm going to look at the minimum. So second calc minimum, number 3. The left bound, I'm going to put it to the left of the valley. The right bound, I'm going to put to the right of the valley. Guess. So the minimum is 6.08, comma 4. So it would be 1, 2, 3, 4, 5, 6.08. So it would be kind of like right there, slightly to the right of that point. So it would be 6.08, comma 3.99. Okay? Alright, so that is the maximum and the minimum. And that says calculate the difference in height between the maximum and the minimum. So that's basically 10, that's basically 10.00 something something minus 3.99. Oops. 10 minus 3.99. So basically it's 6.01. Okay. Alright, so that's the difference in height when the roller coaster rolls from the top point to the bottom point. Last one for this page. A pandemic can be modeled by the equation. And I was just reading about a new pandemic, or a developing pandemic in China. So this is was on my mind. It's called the coronavirus. Scary, huh? Okay, pandemic can be modeled by the equation x minus 15 cubed plus 4,000, where x is the number of weeks after the outbreak started, and f of x is the number of cases reported. Plot the graph of f of x between x equals 0 and x equals 50. Does the graph have a local maximum or minimum value? Okay, so let's type in the equation. So I'm going to erase that one. And then I'm going to put x minus 15. I'll be right back. So I just typed it in. And if I graph it, it's like so tall that I can't see it. So maybe we'll do zoom fit. Let's see how it looks. Okay, okay. We don't really care about the negative part, so I'm going to modify with window. I'm going to say the x min is 0 and x max will be 50 because it says to graph from 0 to 50. So we're going to do that. And then we're going to do a zoom fit. Zoom. Fit. There we go. That's a pretty good picture. All right, and then plot the graph between x equals 0 and 50. So to do that, let's get some values from the table. And if we're going to plot from 0 to 50, we don't need like every single number here. What we can do is we can jump by tens. Okay, and then so this will be 0, See, the left edge here would be x equals 50. So the highest number is 46,875. So I will make the highest number 50,000. And so this would be 10, 20,000, 30,000, 40,000, 10,000. Okay. So the first point is 0,625. So that wouldn't hardly even register. 10, 3,875 would be about here. 20, 4,125 would be about here. 30, 7,375 would be about here. And 40, 19,625 would be about here. There. And last one is 46,875. That would be about here. So, how does that look again, the graph? It looks like it goes up first. And then it goes, oops. Let's try that again. Okay, how's that? All right, so that's the graph, and then it says, does the graph have a local maximum and minimum value? No, it doesn't, because it's steadily increasing, right? Find the number of cases where x equals 20 and where x equals 40, so that would be this point here and this point here. And so we already know that, because we've actually plotted those points, but let's find the exact value in the table. So x equals 20, the exact value would be 4,125. 4,125. And for x equals 40, the exact value would be 19,625. Okay. And state whether this is a suitable model for the scenario and justify your answer. So, suitable model for the scenario. What they're looking for here is you look at the shape and say, is this reasonable? Is this what I see when I imagine like how a outbreak is going to spread? You know, the only problem with this that I can see is, what does it do when it goes over here? Well, this is a cubic, remember. So it goes through like this middle point, and then it's going to go to infinity. And it's going to go to infinity exponentially. And eventually you're going to run out of people in the world, right? There's like, what, 8 billion people in the world or something? When you get to 8 billion, you're going to run out of people, and then obviously the curve is going to go anywhere. Or you're going to run out of people in the country, like this, you know, they're trying to control this coronavirus by keeping people from traveling. If they can keep people from traveling, then maybe it's going to, you know, devastate a certain region, but at least it won't spread across the world. So, yeah, so like eventually you would expect a curve like this to flatten out when it starts, you know, running out of people to infect. So that's what I would say is the problem with this model. It works for, you know, 50 weeks, but the further it goes, then eventually it needs to come down, right? And the cubic model never comes down. So that's what I would say the problem is here. And that's it for this page.